So last time we talked about the let's say covariance matrix estimation under some structured sparsity assumption. So just let me recall what we did. So we had this idea that if you have sparse covariance matrix, in the extreme case, the diagonal covariance matrix, then by thresholding the sample covariance matrix to the diagonal entries, you could do a much better job. So this threshold estimator would have an error rate, which is root log d over n, as opposed to root d over n, which is the bound that you would get, assuming, let's say, d is less than n when dealing with the full sample covariance matrix. And then you ask whether we could achieve something similar if we don't know the sparsity pattern. So this case is not interesting because if things are diagonal, then you wouldn't really be estimating the covariance matrices. You're just estimating a bunch of variances. So you care about the case that there's genuine covariance between random variables involved, but maybe not too much or not too many of them. And so the sparsity pattern, we can assume there is a sparsity, but the sparsity pattern is not known. And then the idea was that we could do the thresholding. So a natural idea was to do this hard thresholding on the entries of the sample covariance matrix. And this would give us an estimator whose deviation from the true covariance matrix and operator norm would be bounded by this lambda times the operator norm of the adjacency matrix of the sparsity pattern of sigma. And so lambda is the size of, as we saw in the proof, a bound on the L infinity deviation between sigma hat and sigma. And this L infinity deviation is in is a pointwise deviation. So what you really what you're bounding is like the maximum of these point like element-wise deviations, and this can be quite small. So you can show using the techniques that you now know that so you do it for every coordinate, and then you do a union bound that this is of this order, where sigma squared, or sigma is a bound on the sub-Gaussian norm of each entry, and so the bound would be root log d over n, which is like the bound that we have for the diagonal covariance matrices if you do the thresholding. But there's this extra term, which is the price that you're going to pay because of the unknown sparsity pattern, or because of the fact that there is some sort of non-zero elements outside that you're trying to estimate, and this would be in the worst case S. Let's say if every row has S non-zero entries, and it could be smaller. It could be like root S for certain like hub and spoke structures, things like this. But in any case, the dependence is much better in D relative to the case where you don't assume anything. Okay, so questions about this? Everything is good. Okay, and then we did the proof. The proof is basically just this deterministic inequality that the operator norm of the threshold that sigma versus the population sigma is going to be controlled if we have a bound like this. And it's a simple argument that you can go through. And then we argued that we could extend these results to the case where the maximum LQ norm of each row of the matrix, or it could be the column. So if you look at each row, basically you're assuming that the ith row belongs to the LQ ball, the LQ ball of radius RQ to the Q, basically. So if you think of the, RQ to the 1 over Q. So this is the LQ norm of the ith row. And so the assumption is that each one is in such LQ ball, and then Q, let's say, is in 0 to 1. Because strictly between 0 and 1 is something which is interesting, because it forces you to, or let's do it like in strictly 0 to 1, such that the entries are not necessarily 0, but there are a lot of small ones. And so in that case, what you could do is you show a similar bound that if sigma hat minus sigma in operator norm is less than lambda over 2, then this operator norm bound holds, and this replaces the 2 lambda a sigma operator norm. Okay, that we had, so replaces this, and then you just replace lambda with the bound that you have on this, which is of this order. And so once you do that, you get that this is like O of something like this RQ lambda, which is root log d over n to the 1 minus q to the RQ log d over n to the 1 minus q over 2. And this is a sort of relatively good rate. You could, at least you can see that the dependence on that dimension is logarithmic. And if I recall correctly, as I mentioned last time, this is also optimal in a sense. Okay. And so what we need to do, which I'm going to let you do it yourself. And this could have been a good homework problem, that you'd show basically the inequality. You can do it simply for vectors. So the idea is that if you have a vector theta hat minus theta star which is close to theta star in infinity norm, in the sense that the deviation, the infinity norm of deviation is bounded by lambda over 2, then when you threshold it, the L1 norm of the deviation would be controlled. And then if, let's say, theta star has a LQ ball constraint like this, then you could balance these two. This is very similar to what you perhaps did in a homework problem for the regression. If theta star is in there, then there are bounds on the size of S. There are bounds on the size of S, and also this guy in terms of lambda and this basically R and Q. So you would be able to drive this. Okay. So what is the significance of this? How can we use a result like this? I'm not going to prove this. You can try to prove this yourself. It's very instructive, even if the proof is down there. But why we can use this lemma to drive this result? Anyone remembers what is the significance of bounding the L1 norm? So here we are assuming that every row has an LQ ball constraint. And what I'm showing is that if you have vectors that are close to each other in infinity norm, then they all, and then the vector is an LQ ball, then the L1 norm is controlled. L1 norm of the thresholded version to the theta star is controlled. So how can we relate this type of result to bounding the operator norm of the covariance matrix? Anyone remembers an inequality for the operator norm that can be used here? So the question is, I have, am I still on or?
Yeah.
Yeah, okay, so you have covariance matrix, every row, you can think of every row here as theta hat. I mean, I can fix one row, and then there's this is the sample covariance matrix, and then there's the population covariance matrix. I can think of the one row as theta star. So I know that theta hat or theta star here belongs to that LQ wall. I'm doing like R here. And then the idea is that then if I threshold this row minus theta star, the L1 norm is controlled like that. Okay, so this result can be applied to each row. But how does this relate to the
I think the infinity norm, I can remember it's the infinity norm or one norm, but one of the norm is the maximum absolute row sum.
Okay, yes, great. That's exactly what we're going to do. Yeah, so so we have, we're going to apply this to each row. So what you're going to get is, take this to be, for example, sigma hat, and let's say I star. That's the, I'm going to drop the n. So I star is the ith row, but this is sigma, the ith row. Okay, so this is saying if I have sigma hat I star minus sigma I star, infinity is less than lambda over 2, that's this condition, then I would have T lambda sigma hat I star minus sigma I star, right? In L1 is bounded by lambda over 2. And so if I have it for, if we have it for all I, then this would be sigma minus sigma infinity less than lambda over 2, which implies that the maximum of these guys is bounded by, sorry, not lambda over 2, but let's say 3R 1 minus Q by this lambda 1 minus Q. And this is one of the two, as I think Shinji, I believe Shinji, was you Shinji, or who said that?
That's me.
Yeah, right, okay, so that was, this is the maximum. Yeah, you can also think of this as basically T lambda sigma hat I star minus sigma, sorry, not I star goes out because this is like a linear, taking the ith row is a linear operation. So if I do this and then do that, that's the first. First take the difference and then take the ith row, or first take the ith row and then take the difference. It doesn't matter. So this is one of these other norms that we have. This is like the I also don't remember. So it could be like the infinity or L1. Double check or this. It's going to be the same for this symmetric matrices. It's the maximum row sum or the maximum column sum, absolute column sum. So it's most likely, well, let me check. Yeah, I think. So this would be infinity, I believe. So L1 would be the maximum column sum, absolute column sum. This is the maximum absolute row sum. But do let me know if this was wrong. So you would prove this, and then there is an inequality. So we have sigma hat minus sigma infinity to infinity is bounded by 3R1 lambda 1 minus Q, and then for symmetric matrices, this bounds the operator norm. So I believe this might be the Bickel and Levinger result that I mentioned. There's this paper. So their idea was to use this inequality to bound the operator norm, and then use this basically row-wise to control basically the maximum row sum. So you can control the maximum row sum using the this argument that we did. Okay. Questions? So the rest of the details I'll let you follow. This is a little bit different than the approach that we use here. So here we didn't use the that inequality. We used an alternative inequality that if you have a pointwise bound, then you can translate this pointwise bound to an operator norm bound. So that was a combination of these two. So the basic underlying inequality between the two cases is different. So this is a better result. So you could have used the let's see. Yeah, I believe you could have used that result, but you would get, instead of the operator norm here, probably you would get the infinity to infinity norm. So you would get the maximum row sums of the A matrix, which is like a looser bound. So this argument is a little bit more it's tighter, but whether such an argument can be used here is debatable. Okay, sounds good. So to recap, doing covariance estimation, sample covariance is quite good in general. And then if you have a sparsity, a very simple modification, which is just thresholding would do. Here thresholding, you could like take the maximum, like K largest element, but here we're doing like a proper thresholding. Instead of choosing how many we choose, we're just setting a threshold and just set everything below the threshold to 0. And the idea is that if you choose the threshold properly, at least this much, so the size of the threshold should be this much, at least this much, but not bigger, then you would get a bound which goes down to 0 with logarithmic dependence on the dimension. Okay. Questions? Comments? So as an exercise, try to do this lemma 6 yourself and see if you can figure it out. It's a good exercise in understanding the LQ norm constraint. Okay. if not, I'm going to move on to, so you guys didn't all vote, so you get to let's say, experience what the few that voted decided. So like 9 people voted, and we have like 56 to 44 for non-parametric regression. So it's very close, but as of now, non-parametric regression wins. So we're going to talk now about non-parametric regression. Okay. So, so let's see. How many of you know about non-parametric regression? I've seen it before. Know what it is? Okay, Naveen. Anyone else? You can like raise your hand in the chat, or only Naveen has seen non-parametric regression. So, Naveen, do you want to say what it is?
Yeah, it's basically, I mean, as the name says, it's when you're trying to perform regression, but without like a given functional form for your sort of like the way you estimate the data. So, you know, linear regression assumes like a linearity in the parameters, whereas if you were to think about like the cost function for a non-parametric problem, you would just have like y minus some theta, and the theta doesn't have a form, it's just an estimate.
Okay, so let's unpack. So the first is regression without a particular form, not like regression, like linear regression that assumes a linear, let's say, form for the function. Okay, and then what was the last thing about that? That was correct, right? So that's like assumes a linear form for, yeah.
I guess you're basically trying to directly estimate any given value in your function. So like, yeah, you would just have yi minus theta I instead of some kind of
right. So I minimize this, let's say, but well, if I minimize this, then the solution would be like theta hat would be just yi. So is that a good?
Right. I guess you also have to assume some kind of constraints in order to so like you could assume like sparsity in the differences between the theta i's, which I think is like total variation denoising.
Okay, great. This is great. So you went like further ahead. So we're gonna get to this. This is great. So we'll talk about this. Yeah. So we need, if you do this, you need constraints on theta. Without constraints, you would get like a trivial estimator. So let's say Evan also mentioned that you mentioned that you also heard a little bit. So can you maybe say, what did you hear about non-parametric regression? I'm curious.
Yeah, I guess, I mean, I know I've heard like thinking about functions as almost like vectors, like infinite dimensional vectors.
Functions is infinite. Okay, great. Infinite. Then, so functions as infinite dimensional vectors is like a general idea in math, like functional analysis, basically. So how does it relate to regression?
I forget exactly, but I feel like you can, like they're similar. I guess is Gaussian processes sort of treating it like an infinite dimensional vector?
Okay. Yeah, there are, okay, Gaussian processes. Yeah, the Gaussian processes are basically everything. So you could sort of tie a lot of math into Gaussian processes. So you could view this as Gaussian processes have a lot of different interpretations. So there's definitely a relation between viewing functions and infinite dimensional vectors and Gaussian processes. So this is good. So this is like a different viewpoint. One idea is that, so we will see aspects of this. So viewing functions as infinite dimensional vectors, what I want to maybe mention is that there's a different problem. So there's a problem called functional regression, or general functional data analysis, in which you would assume that you observe entire functions. So your observations, these would be in some functional space. And then there is a certain mean to them. So the expectation of these would be like a particular function of interest, and then you want to estimate this. So this is more in this spirit of viewing functions as infinite dimensional vectors. Of course, in practice, you don't get to see entire functions. So there is some sort of a degree of abstraction here. This often is used, for example, if you have like a very finely sampled data, you might assume that, oh, I'm observing the entire function. But I want to make sort of this was a good discussion. Let me ask anyone else. Anyone else has sort of any comments? Because I mean, this at least highlighted two different type of problems that we can think about. One, which the one that Naveen mentioned is more closer to non-parametric regression. This one is closer to functional regression, and they're sort of related, but a little bit different. So maybe I'll talk about this a little bit when we talk about. But this idea of viewing functions as infinite dimensional vectors is going to come up in either case. So anyone else has any sort of other comments about non-parametric regression? And then Gaussian processes also come up. There's this, yes.
I guess maybe just to add on to the functions as infinite dimensional vectors, could we bring in sort of kernel methods and
Okay, yeah. So there is this link between non-parametric regression and so kernel methods. So let's do this. Say non-parametric regression. Regression. Functions as infinite dimensional vectors. This is one idea. This is statistical idea. Kernel methods. This is another idea. And then functional regression, which is another idea. Okay, so functional regression is related to this. Functions and vector like infinite dimensional vectors, and so this and the kernel methods are related. This is via this idea of the RKHS, reproducing kernel Hilbert spaces. There is this idea that floats around Gaussian processes. So this guy is also related to both of them, very intimately related to, so let's call this maybe this is another idea, which is, so to be honest, it's a little bit separate from kernel methods. Okay, you can view kernel methods like it's just kernel tricks and things like that, but mathematically, if you want to view it, the real connection is, so this is that. And then the Gaussian process is also like connected to both of these ideas. So functions as infinite dimensional, you can think of Gaussian processes producing random functions in infinite dimensional spaces, and Gaussian processes also define RKHS. So there's this RKHS associated to every Gaussian process, and the properties of the Gaussian process and the RKHS are very intimately related. And there's this relation between these two, which is called Gaussian process regression, GP regression. And this is also related to the kernel methods. So everything is sort of related. I can't do a good job of drawing this, but all these ideas have connections to each other. So what I'm going to talk about is nonparametric regression, but aspects of these ideas would come in. I might talk a little bit about this idea, yeah, so there should be some sort of a so an example is like the connection, the direct connection between these two would be like kernel ridge regression. Yeah, not a nice diagram, but think of everything is connected, but sort of a little bit. So the central idea is like the functions as infinite dimensional vectors. This is going to come up very often. So let's try to do the maybe do the nonparametric regression model here. So nonparametric regression is like the idea is that you have this function in some function space. This is a function class, and you get to observe its samples at a certain set of points, but you observe the noisy samples, something like that. Or a little bit more generally, you observe y more generally. Doesn't have to be observe y with the expectation of yi given xi being f star xi. And then you can say, for example, that the deviation, you can define the deviation to be basically yi minus f star xi. So you can write like something like that, but the noise could also depend on xi or f star of xi. So it doesn't, and then you assume that the epsilon i's have good properties. The simplest case is just assume that let's say epsilon i's are normal, which means 0 and variance sigma squared. But more complicated models could like this could depend on the mean as well, or on xi as well. So what is the relation between this and the usual linear regression? So linear regression. So how does linear regression relate to this nonparametric regression? So nonparametric. How does linear regression relate to this?
Our function is just like xi times beta.
Yeah, okay, so f star is a linear function, is assumed to be linear. Or rather, f is assumed to be the class of linear functions. The class of linear functions, or functionals if you want, functions on RD. So this is the set of all functions such that from, let's say, RD to R, that f is linear. Then you would know that any linear function, so this would be the class of all functions that can be written as f of x is equal to beta x for all x in RD and some beta in RD. Okay, then f star can be written as like beta star x for some beta. And then the problem reduces. It reduces to estimating beta star. What you get is yi equal beta star xi plus epsilon I, which you can write as y is equal to x beta plus epsilon I if you put these as rows. So you observe a sample size n, I from 1 to n. This just collects. Y would be y1 up to yn, and epsilon would be epsilon 1 up to epsilon n. Okay, so you've seen this. The reason why this special case is usually called, this is like parametric model. A parametric model is because it's parameterized by a finite dimensional. So this class is parameterized by beta, which is a finite dimensional parameter. So estimating functions in this class is not more difficult than estimating a d-dimensional parameter. We can further restrict this class of linear functions by restricting beta. As we've seen, for example, you can put a sparsity assumptions on beta that would restrict the class of linear functions that you would observe. So it would be functions that are only dependent on a certain number of coordinates. Linear functions that are, the subclass of linear functions. Linear functions only depend on a certain number of coordinates of the input. So this is a special case of a non-parametric regression. It's not called non-parametric because the class is, as I mentioned, parametric. What you care about is in non-parametric regression where this class cannot be stated or parameterized by finite dimensional parameter. Generally, the class is too big, and often the class is infinite dimensional. That's really what people call non-parametric regression. So this class of functions is infinite dimensional, and the idea is that by making this class big enough, I can make sure that I'm not imposing unnecessary assumptions on the regression function. So you might know that this is a very severely limited class. The space of all functions is much richer than, and especially on RD, is much richer than just linear functions. And so by removing that assumption and letting AF be a more genuine high dimensional, the infinite dimensional space, you would get hopefully much better fit to reality. The difficulty is that if you make this infinite dimensional, then the question is, how can I estimate something which is possibly in an infinite dimensional space given a finite sample size n? Is there any hope of estimating something like that? So what do you guys think? So if I make f infinite dimensional, can we estimate anything? Is it doable? That seems like a paradox of statistics. So you always get to see a finite set of observations, but you would like to estimate possibly infinite dimensional objects. Is it?
I guess not without constraints, maybe.
Okay, good. Yeah, not without constraints. So if I so if you let the class to be like any function, then you might be able to show that no matter what you do, there exists something in the class that would make. So there are these ideas of looking at. So can it be done? Basically, non-parametric regression, where f is infinite dimensional. If I so if you make the class if you make the class too big, the class too big, say f is the set of all functions on RD, because you might always find a function and it also depends on your measure. Also depends on your measure of performance. Okay, we'll see this or discuss this. Performance. But yes, if we impose some restriction on f, and I'll talk about examples of restriction. Usually the restriction comes in as a form of smoothness. So if I put some sort of a smoothness, usually some sort of smoothness, then I would be able to recover things. So this is an interesting point to have in mind, that this is what we are trying to solve is actually an interesting problem. So you're trying to do like estimate an infinite dimensional object based on a sample of size n, and depending on the measure of performance that you choose and the class f that you choose, this may or may not be possible. Okay, questions so far? So what is a natural estimator? Let me maybe mention this. So what is an estimator that you propose in this case, if you want to, before determining what the class is?
You would basically like do yi minus theta I, and then you penalize the differences between each theta I, and so you could penalize them either by like an L1 penalty or L2, and the L1 penalty will like give sparsity like it does for regular linear regression, so it'll make like a piecewise constant sort of estimate.
So you'd say something like L1 of this, something like that.
Yes.
That or okay. This is good, but I'm not right. So this might be good for certain classes of functions, and in particular, it would be good for like piecewise constant functions. So if f was say say Naveen's estimator. So good if F is the class of piecewise constant function. So this class is, let's say, so this is good if, let's say, xi's are, so D is 1. So xi's are in R, and you think of functions in the real line. So the function could jump sort of to a certain point at some point, but it's constant between these knots. So let's say it could be like negative here, and then goes here, and then here, and then maybe down there. So you know that when you penalize things by the L1 norm, it tends to produce a lot of coordinates that are 0. So in a lot of coordinates, you'd get that this difference is 0. So the function would be between like xi minus 1 and xi would be constant. And so if you assume the function has this form, this is a good penalty. But let's say in higher dimensional spaces, and if the function is not of this form, maybe this is not. So the form of the penalty is dependent on what you assume. So what I was hoping for is like more general. So you can say, if I'm doing from this class, I'm trying to estimate from this class, I just impose that as a constraint. I'm going to try to minimize this. This is a more general, so more general, let's say, projection type estimator. You could also do like a penalized version, obviously, not obviously, but so if you have a proper norm or some sort of a measure of this class, it could be dependent on the class, or it could be. So let's say I have some norm that measures being in this class. So so let's say F is small when I'm within the class, when F. So let's say F is finite, if you want, something like that, when F belongs to F. Okay, so I have a norm which imposes sort of, or measures in a more soft fashion whether it belongs to the class or not. You can sort of try to penalize them. So this is a little bit more general. And so when your class, for example, is piecewise constant, you might think of this as, there could be some like alpha here, some other power. You can think of this as some sort of a an approximation of a norm in that class. This sort of is an approximation of, let's say, the total variation norm, which is a well-defined norm. Okay, so what we're going to study is an estimator like this, or a penalized version like that. In fact, we're going to mostly work with this version, the simplest version. Okay, so this problem is a little bit abstract, but we want to see what we can say on the performance of this estimator. So this would be like f hat. It could be there could be multiple solutions, but let's say a solution f hat which belongs to class F and minimizes this sort of goodness of fit criteria. Okay, so we're interested in analyzing performance of these type of estimators. Okay, so far so good. Okay, so estimators. The other one is like the measure of performance. I'm going to get to this. So let me just point out that the RKHS, or the RKHS connection, a little bit here. So detour. So how many people have seen RKHSs or kernel methods, things like this? RKHS, kernel, okay. Naveen, anyone else? So Hilbert spaces, math people should have seen these, right? So kernel methods. Kernel ridge regression. So kernel ridge regression is an example of something like this. The regularized version. So this is, the case is like you assume F to be H, which is a Hilbert space of functions. What is a Hilbert space?
It's a space with an inner product defined on it.
Yeah, so it's like an infinite, potentially infinite dimensional Euclidean space. So there is an inner product defined on it, which makes it into a complete norm space. But the idea is that there is the inner product, and like things are orthogonal, and it behaves like a very like an infinite dimensional. Like you have orthogonality, and you have the usual notion of geometry. So there is a vector space with an inner product that makes it complete. The completeness is because like we care about like convergence sequences and things like the Cauchy sequences converge basically. And so it could be infinite dimensional, and usually it's more interesting when it's infinite dimensional. And then an RKHS is a Hilbert space of functions. So Hilbert spaces could be abstract, but you could have Hilbert spaces of functions. And in fact, there originally was the idea of Hilbert spaces was introduced to study the spaces of functions. Hilbert spaces. It's a Hilbert space of functions such that the evaluation functional is a continuous / bounded operator. So in infinite dimensional spaces, linear operators could be unbounded, and you care about bounded operations. So the idea is that what is an evaluation functional? Evaluation functional is like a map that maps H to R, and when you apply it to a function in the Hilbert space, it takes it outputs the value of the function at X. So if you evaluate the function at X, you can view it as an operation. So this is a linear functional, and you can easily see that it's linear functional. So if I add two functions and I evaluate them, the result at X is like adding the f of X plus, let's say, g of X. So it's a linear functional. And in an RKHS, this is delta X is a bounded operator, which is equivalent to being continuous. Is a bounded operator. So it means that like delta X supremum over, so the Hilbert space has a norm. This is bounded. This may seem something abstract, but because of this property, that this is bounded for every x. So every evaluation functional sort of fixes x and just evaluates every function at that x. And so for every x in the RD, let's say, so these are functions from RD, let's say, to R. They could be more general. But because of the fact that these functions are in an RKHS, they're bounded, they need not be bounded. First, they're well defined. So let's say if you look at the L2 classes of functions, they're not really functions, so you can't evaluate them. They're like equivalent classes of functions. So you can't evaluate them at the point. So RKHS is the functions are the value at each point matters. So the evaluation function is well defined and is also bounded. And so there's this theorem called I believe Reed's theorem, or I can't write his name. That every bounded functional can be written as sort of another member in the class, like in the Hilbert space. So every bounded function, just like the RD, you can write it as let's say H times F, where H belongs to the Hilbert space. So there is a member of the well, let me call this maybe K of X, where K of X is just a member of the Hilbert space. Okay, this is like the thing that we mentioned here, that every linear functional or linear function can be written as beta times X. This is an example of the Reed's theorem. It's obvious in RD, but you can replace this with the Hilbert space and this with the inner product in the Hilbert space. And so that generalizes to every Hilbert space because of the assumption that since this is bounded, there exists an element of the Hilbert space depends on this X, but this X is fixed, such that I can evaluate the functions by taking the inner product of that vector with the function. And this is very useful because why this is useful? Anyone? Because it just turns everything into, like, if I can think of the evaluation function as inner product, you can imagine my regression like problem, which was f star xi plus epsilon I. If f star is this RKHS, then I can write this as k xi times f star, right? And this looks very much like usual regression, where you had like beta star times xi. It's just we turned the evaluation into inner product, so you can think of this as you're basically viewing y, and you can think of putting them. I mean, you can think of transpose, but it's like a little bit. It's not good to write it as transpose. I'm going to write it as transpose to make no transpose here, but what we're doing is like when you multiply this by f, you should treat the kx I transpose f star as just to mean the inner product between this. And so there's this is like infinite. This is n, so n by infinite dimensional. So you can view this as just a usual linear regression, but the design is like a little bit extended, okay? And it turns out also that this guy can be written as a function. There exists a kernel function such that this can be written like this, and this belongs to the Hilbert space. So every RKHS has a kernel such that this evaluation function, like these are representers of evaluation, basically. Representer. of evaluation. These can be written. So moreover, there exists a kernel function k dot I mean from r d times rd to r, unique to every RKHS, such that you can write these representers as these viewing as these kernels, fix one of the entries as x and view this as a function of the other entry. That would be the representer evaluation. So you'd have like basically k x f a star would be f a star x. So I can write these as basically these are, we can just imagine. So these are known. So for RKHS, you know the kernel, so you know these evaluation functionals, and in particular, if you apply this identity to, let's say f a star, let's say be another one of these functions, this would give you kx x a star. So this is a symmetric function. So you would get these kernels. And so you can form the inner product of these in the Hilbert space, and you'd get just the kernel evaluated. And you can see, let's say if I want to do usual regression, I would say that basically f a star is like, if I call this x, you'd get x transpose x inverse, x transpose y basically. And so this would be like this kernel matrix. So if you do this, you'd take the inner product of these entries with each other. So this would be a matrix which looks like this, which is called the kernel matrix. That's the kernel trick basically. And then this one would be so you can figure out what this is. I'll let you figure out what this is. And so if you do try to do regression here, you would get something like that. And so far clear, is it? I didn't want to go this far into this idea, but is it clear, sort of? So what you would do if you try to argue like this, you'd run into some problem that in this, if you try to do the least squares alone, so if we try to solve this restricted problem, minimize f in the Hilbert space, this would turn out to have many solutions. So this is really an infinite dimensional space, and so you would get many f hats such that f hat xi is y. So you can interpolate perfectly all these points. So in practice, what you would do is you define a regularized version, argmin 1 over n sum I from 1 to n, yi minus fxi squared plus lambda. You impose the Hilbert norm. And this is the kernel ridge regression. Or you could try to do like f hat interpolation, which is minimize the Hilbert norm subject to interpolating the points. This is not statistically, or at least up until a few years ago, this was not necessarily a good idea in statistics to try. So you could do it. So if f is in Hilbert space, you can always interpolate any, if f is infinite dimensional. There are many functions in the Hilbert space such that, so infinite dimensional RKHS, then you can always interpolate any n set of points. And then the natural thing to do is to find the minimum norm solution. And these ideas are very similar to ridge regression and minimum norm solution that we started like talking about in the finite dimensional case in the first lecture. These came up. And nowadays people would think these interpolation estimators are actually interesting. Any case, so this is like a quick detour into the RKHS. So that's one class of function that you can analyze. And for example, an example is, let me just give you a very quick example here. There are these Sobolev spaces. Sobolev space, like order 1. So the class of all functions such that f, let's say from real to real, f is 0, and then the second derivative squared is finite. Okay, this class of functions is an RKHS. The inner product would be just integral of f prime g prime dx, and the sort of the norm here turns out to be just integral f double prime dx, and so this measures some sort of a roughness. So the more smooth the function is, the smaller the norm, and so the f hat lambda, this guy, becomes some sort of a interesting object. So you do this would be integral from 0 to squared dx. So you'll be solving this argument. Sorry, this is not the second derivative. Order 1 is just the first derivative. The second derivative. This is if it's order 1. So if it's order 2, then it would be second derivative. So this is okay. So if you solve this, so this is a solve of order 1. What you would get is basically this would be yeah, let's not worry about this. What it would look like. So that's one version. Then you could also sort of do like order 2, for example. This would be double prime. These would be double prime. This would be double prime, and this would be the double prime version is called smoothing spline. So the solutions would be like what they call a smoothing spline, and you can also sort of solve all these problems because they're examples of this, and they're closed form solutions for this problem. So it might not look like how do I like deal with this, but because it's an RKHS, you could reduce it to this, and the solution of this can be written in a very nice fashion using this representer ideas, because you can turn it into a finite dimensional problem basically, and then you can solve the finite dimensional problem. So I'm not going to go into that much. I just wanted to give you a taste of what this looks like, and we ran out of time almost. I just want to mention like one last thing before next time we're going to come and actually analyze these things. And if you have questions, let me know. We can sort of come back to the RKHS connection later, just to give you an example. So performance measures, what you can do is like you can do like L2, real L2 norm. So let's say I have my estimator. I can try to measure its distance to the truth as like, this is common, minus f star x squared dx. The other measure is like the empirical L2, which is what we're going to work with. Empirical L2, which is written sometimes like this, n2. This is the, it's better to write it like as L2 of p, you could say. Could have some sort of a distribution on x. This is going to be L2 of Pn. This is the empirical measure, which is just the measure that puts equal mass on all the data points. This would be equal to integral f hat x minus f star x dPn of x, which is just the summation I from 1 to n, f hat of xi minus f star of xi. And these xi's are the training data. So you just care about the deviations in the training data squared. And so this guy, you can see that this is very close to the actual L2 norm for large n. But we care for this norm because what you really can estimate are these values of f star valued at xi. You can't really estimate anything outside. So if you look at this, the actual model that we have, the model is identifiable for these values, the values of function at xi. The values of f naught at xi are not identifiable. So any other function that has these values at xi and is different elsewhere is going to produce the same yi. So the identifiable component from for this model is the value, like f stars evaluated at xi, and so that's the natural like statistics norm to deal with. But people often care about this. They call this like the real or the generalization norm. This is, they can think of x as the new data point that comes in, and you don't know the actual, you haven't seen it in your observations, and what is the expected sort of, this would be, so this real L2 norm would be just the expectation of f hat x minus f star x for a new data point that comes in. And so this is sort of also interesting. Okay, so we're out of time. Sorry for going over a little bit. Any questions, comments? So this was a setup. Next time I'm going to come back and we're going to start from this and then try to build some reduction, make some reduction and build some theory. So how do these estimators behave statistically? Okay, sounds good. Okay, sorry that we went over time, and thanks for staying around, and see you next time. Okay, don't forget to sign up for the project.